So, hi guys, I'm live. How you guys doing? I think it's time for a math lesson. I've been saying I would do another one. I like to do what I say I'm going to do, and I say it because I intend to, and I like to do what I say I intend to do. So this lesson is on implicit differentiation. In the subject is calculus, but implicit differentiation is what I want to cover this time. I've got a few examples. I've got a book here to keep me on track, and in the examples, I'm going to do 3 of them. Keeps me make sure I get the right answer, and then I don't go, rogue or off the rails and not know it. Okay. So, let's talk about math for a second. Math has constants and variables. A constant can be 5, a constant could be pi, a constant can be e, a constant can be I. That's a rhyme. So having a letter doesn't necessarily make it a variable. Letters can represent constants as well as variables. It depends. And letters at the beginning of the alphabet usually represent constants. Like E is toward the beginning of the alphabet. I, beginning of the alphabet. Pi is a Greek letter. But then there's also variables. A variable is not a fixed value. It can be anything you say it is at the time, not necessarily one thing all the time. And in that, we usually use letters at the end of the alphabet, X, Y, Z, like y equals f of x. Well, obviously y is not a number. It's a function of this thing x, but that's not a number. It's a variable. It could be anything you put into it. And notice that x and y are toward the end of the alphabet. So there's constants and variables, but just because you have a letter doesn't mean it's a variable. Doesn't mean it's a variable. Letters especially letters at the beginning of the alphabet can be constants as well. E is approximately 2.718281828, and I don't remember the rest. Of course, I could not remember all of it because it goes on infinitely, and I don't have an infinite brain. But that's a constant, not a variable. And it's such. I equals the square root of -1. Well, that's not a real number, but it's also not a variable. It's a constant. It's one number. And I is toward the beginning of the alphabet. And then you have things like, I'll just say pi for now, since I brought it, is 3.1415926, and goes on and on. That's just the ratio of the circumference of a circle to its diameter. And that's a constant, not a rational constant, because it doesn't have a repeating or terminating decimal, but it's still a constant. It also happens to be what's called an, what do you call it again? Transcendental constant, as is I. I'm not enough of a math geek to know right now what a transcendental means exactly, but I know it's the opposite of non-transcendental, LOL, and it's another variable. It's another property the number can have that makes it exotic, or not just like 1, 2, 3, 4. Anyway, there's some, and then in math, we have between variables we have functions and relations. What the hell does that mean? Well, a function is like f of x equals, or y equals f of x, where if you plot it on a Cartesian plane as x, this is not the imaginary axis, imaginary plane here. This is the coordinate plane, xy, different than the complex plane that I've talked about a lot, where this is the real value and this is the imaginary value, and whatever dot you're on, point you're at is whatever the real part is plus whatever the imaginary part is. This is two variables that can be related based on a graph. This is called a Cartesian graph, or Cartesian plane, whereas the complex plane is often called an Argand diagram, or the complex plane. Not an airplane, P-L-A. Actually, it is spelled like the airplane. It's P-L-A-N-E, but it doesn't mean a flying craft. It means a two-dimensional surface or whatever. So what's a function and what's a relation? A function is any relationship between y and x such that for any given value of x, there's one and only one value of y in the domain of the thing. So if I say x is this, y is this. For every one x value, there's one y value. Not 2 and not 0. Well, it can't be 0 because it could be out of the domain of the function. This is the domain and there's the range. The domain is the x and the range is the y, I think. It's one or the other. So when I say domain, I mean this way. So each value of x has a single value of y in the domain of the function. I think the x is the domain and the y is the range. I didn't look that up, but I think so. So it's called the vertical line test. If you draw a vertical line through it, you're only going to get 1 point at a time. Only get 1 point. And that's called that if it passes the vertical line test in the domain of the function, then it is a function. Okay, easy enough or clear enough? But then there's a thing called a relation. That's where x and y are related, but not there's more than one y value for some of the values or all the values of x. And in this case, it fails the vertical line test, for instance. In other words, you have a circle, let's say that circle is y equals x. That's not that I started off wrong. Let's make it x squared plus y squared equals 25. Now that's a circle with radius 5. But a circle fails the vertical line test. You can draw a vertical line through it, and you have two values of y for any given value of x in the domain of the function. So x and y are related, but they're not a function. So it's called a relation. They're related, but not one-on-one. The dude has two girlfriends at once. In other words, but yet when you have a function, it's a certain, you can find the derivative of y with respect to x, and it's called explicit, or you could call it explicit differentiation. But then there's something called implicit differentiation, where you find the derivative of y, prime, or when x and y are a relation, but not a function. And when that's the case, such as finding the derivative of this, it's called implicit differentiation, and that's the topic of this lesson. Hopefully I pulled it off and whatever. So let's do it. This is our first example. Make sure that's the example they have in the book. Okay, I'm just going to wing this. What do you want? X squared plus y squared equals 25. Find f prime of x. Or y prime. Find the derivative of y. I didn't bone up on this too much ahead of time. I just looked it over. I just checked it out quickly, and I didn't really plan it out loud. Let's just try to do this. I'm a little nervous about it, because what if I mess it all up? What do we do with this? Thinking. Let's rewrite it as x squared plus f of x squared equals 25, as if that helps. X squared, we can use the power rule. That's 2x. Plus, I have f of x squared. I'm taking the derivative of both sides, I believe. But what is the derivative of f of x squared? The chain rule, I think, will apply. The derivative of 25 is 0 because it's a constant. The derivative of a constant is 0 because 25 is 25x to the 0, and 0 times 25 is 0, and x to the minus 1, so it comes to 0 by the power rule. because 1 is x to the 0, and when you multiply the 0 by the 25, in this case, you get 0, meaning the derivative of a constant is 0. As though we're looking at that as a constant, it's just a flat, straight line, and it's not going up or down, so the derivative of it is 0 because it doesn't have a slope, it doesn't have a positive or negative non-zero slope. It has a 0 slope, therefore the derivative of a constant is 0. Now, the hard part is in between here. Let's do it. I'm going to use the chain rule. So let's say I want to know let's call z of x, which is this. I want to call it that. It is, no, z of x. It doesn't make any sense. Well, maybe it does. No, it doesn't make sense. F of z, I'm going to call z equals, f of z equals z squared. Am I clever or what? That's true. If I call this z, then f of z is equal to z squared. Maybe I should say, let's not call it, let's make it more correct. Let's make it z of x. No. It is literally z squared. Yeah. Okay, I dig that. That z looks like a 2 though. But z, f of, oh. Oh, I goofed up. Let's do this. Let's try again. Let's try again. Z equals u squared. Let's do it like that. Z equals u squared. Let's make it f. Let's make it f of z. All right, let's do it like that. But f of z equals u squared, but u equals f of x. Okay, fair enough. We're going to call this thing u. So f of z equals u squared, but u equals f of x. The chain rule says that f prime of z equals, first of all, equals, it is dz du times du dx. Works for me. Let's erase this so I can have more room up here. But we did make some progress, no? Do I want to do all that? I have to, yeah. Let's just do this. All right, let's do it. So we have this. We have f prime of z equals dz du times du dx. But so f of z equals u squared. So f prime, let's just make it a little more, let's not write it that way. Let's say dz du equals 2u by the chain rule. 2 times 1 is 2, 2 minus 1 is 1, and something to the 1, u to the 1 is u. Oof. Now du dx equals du dx. What did I say that u was? Du dx, since u is just u is u, so du dx equals 1, because the derivative of u to the 1, which is u, 1 times 1 is 1, 1 minus 1 is 0, that's 1, u to the 0, but u to the 0 is 1, so it's equal to 1. So there you have that. We're making progress. Therefore, f prime of z, let's make it so I have more room here. F prime of z equals 2u. I'm doing this right. But u equals, okay, but u equals y. U equals y. So, okay, so okay, hope I'm doing this right. So d the f prime of z equals 2 is y. So what do? Let's do this. I start with the original relation, not function, but relation. X squared plus y. I hope you guys can see this. I'm kind of in the way, aren't I? Derivative of x squared is 2x. Derivative of y squared is wait a minute. Yeah. Two x plus, wait. It's been a long time since I've done calculus. Am I getting rusty? Okay, x squared plus y squared equals 25. So yeah, make that worse. Y squared is 25. Let's do it like this. Let's go y squared equals 25 minus x squared. Let's start. Let's do it like that. Sorry for the... Now, what is the derivative of y? So I say the derivative of y squared d y prime equals hold it a second here. Okay, what am I doing? Y prime dy dx derivative of both sides. Okay. I said that I said y prime before. I said y prime was y, didn't I? Y dy dx equals y. I think I said that. Because 2y times y, the derivative of y. Oh God, am I stuck? Y squared dy. take the derivative of y squared. Here, let's do it like this. Let's try it. So I can take the derivative of both sides. 2y, derivative of 2y. Derivative of y squared is 2y times the derivative of y. That's it. Dude, oh my God, I'm so stupid sometimes. If you have z equals y squared, then dz dx equals 2y times dy dx. Oh, that's the answer. Okay, you guys get that. If I make z y squared, then dz dx by the chain rule is 2y times dy dx. Because dz dx equals dz du times du dx. Dz du is 2y. Du dx 2y z du. U is y. Yeah, but u is y. So du dx is dy. Yeah. Let's go with this. Dz dy times dy dx. Okay? This is z is y squared, so dz dx is 2y, which is dz dy, which is 2y, and then dy dx is multiplied by that. So what you have is this derivative of this y squared is 2y dy dx. See that? 2y dy dx. So I'm going to write (2y dy dx). I'm not erasing this stuff very well, am I? Dy, derivative of y squared is 2y dy dx. Equals, derivative of 25 is 0. The derivative of minus x squared is minus 2x. See that? By the product rule. 2 times minus 1 is negative 2. 2 minus 1 is 1. X to the 1 is x. So this is a 2. See that? That's how I'm doing this right. Then I can solve for dy dx. Dy dx equals negative 2x all over 2y. The 2's cancel out. So dy dx equals minus x over y. That's dy dx. It's not a function, it's a function of both x and y because you have a relation, not a function. Moment of truth, dy dx equals negative x over y. And I did it right. So that is derivative of dy dx equals negative x over y. And that is an example of implicit differentiation because you started with a relation, not a function. Okay. Now, any more else on that problem? Because I did that part right. We want to do, let's draw at 0.34. So let's do a little fun thing, as if this isn't fun already, right? Negative x over y I did that right, actually. I didn't rehearse it, or did I just read the book about it either. So you have dy dx equals negative x over y. What is the equation of a line of the tangent line of x squared plus y squared equals 25, tangent line 2, not of, but 2, at the point, what did they say again? 3, 4. So at the point, this is a secondary problem to this. At the equation of the circle, x squared plus y squared equals 25, what is the equation of the tangent line to the circle at the point 3, 4? Let's do that. I wrote the problem out. 3, 4 is the so let's do it. Or not and say we did, lol. So the point is 3, 4. What's the equation of the line? Tangent to the circle, x squared plus y squared is 25 at the point 3, 4. There's such a thing as, I'm going to use the point slope equation or form of a line. If m equals point and the slope, point slope, okay, point slope. M is the slope equals the circle, and you have a point, 3, 4, then slope, point slope. The slope equals y minus 4 over x minus 3, I think. Because the derivative, oh, minus this, sorry. Wait, no. Wait. I want the point slope. This is the slope, m's the slope. It's often used for slope, m is. Y minus, okay, this plugs in. Slope is y, is rise over run, so y minus 4 is the rise, x minus 3 is the run, because the point is 3, 4. Yeah, I like that. All right, doing good so far. But what is m? M is equals dy dx at 3, 4. That's what m is. Fair enough. But if dy dx equals negative x over y, but we just said that we're doing the point x is 3, 4. So x is 3, y is 4. So the derivative, the slope at 3, 4, that point is minus 3 over 4. Because x is 3, y is 4. And the derivative of the slope is the derivative, and this derivative of the dy dx, the slope, is equal to minus x over y, but x is 3, y is 4. So dy dx equals negative 3/4, which is m, the slope here. Fair enough? So now we have, do some erasing here, negative 3/4. Don't forget that number for the rest of your life, lol. Negative 3 over 4 equals y minus 4 over x minus 3. Solve that, and you have the equation of the line of the tangent line to the relation x squared plus y squared equals 25 at the point 3, 4. So let's do some erasing here. And this is minus, by the way. I forgot. Yeah, minus 3/4 equals minus x over y. Wait, that was x over y. It was x over, yeah, x over y. So it's oh, wait. No, that's not true. Come on, Jim. I just want the m equals, yeah, that's right. Slope is minus 3/4 equals y over x, the rise, over x minus 3, the run. Solve this for y, and you have that line's equation, or the tangent line's equation. Let's do that. So minus, see this? Minus 3/4 equals y minus 4 over x minus 3. Solve for y in terms of x. Let's do that. I'm going to cross multiply, which is also called multiply extreme means by extremes. -3 times x minus 3 equals 4 times y minus 4. It's a 4. All right, see that? And then, let's see, 4 minus 4. -3x plus 9 equals 4y minus 16. 4y minus 16 equals -3x plus 9. y equals -3x plus 9 plus 16. 4y equals -3x plus 25. All right, hope I did this right. So let's erase. If I didn't do it right, I got to do it right. Again, I got to do it again. Like, wrong, do it again. Wrong, do it again. Like the end of The Brick in the Wall Part 2 by Pink Floyd off the wall in 1979. Wrong, do it again. Wrong, do it again. If you can't hit your meat, you can't have any pudding. How can you have any pudding if you don't eat your meat? Okay, so for 4y equals -3x plus 25, divide both sides by 4. Y equals -3x plus 25 over 4. I think that might be it. Let's see. I did it right, I think. Oh, I know what I don't have to do it like that. I don't have to do it like that. I can just do this. Let me be simpler than that. The book did, why can't I, right? 4y equals -3x plus 25. Let's just do this. Let's just say that 4y plus 3x equals 25. Leave it like that. I just put the 3x on the other side. 4y plus 3x equals 25. That is equation of the line of tangent to the circle, x squared plus y squared equals 25 at the point 4, 3. Point 4, 3. Let's see if that's right. Yeah, okay, fair enough. Or you could, and of course you can write it also. 3x plus 4y equals 25. Doesn't matter which way you do that. So that's the answer to that problem. And we did it. We did some implicit differentiation and even did an auxiliary problem within that. I could do 2 more examples, and then again I could also kind of just spend all day doing this. And rather than, even though I said I was going to do 3 examples, I think 1 is sufficient. It covers the material. Two more examples would just be exercising that, what we've already done, and showing we can do that too. But we've already done that in this example. I think it's good enough. So love you guys, peace, love, and rock and roll.